Good morning. This part of the lecture will explain how to obtain maximum hover performance. If you remember, to improve the hover performance, one has to minimize the induced drag. The optimum, the lowest induced drag, occurs for an elliptic distribution of the lift from tip to tip. This is according to the lifting line theory. Therefore, minimum induced drag corresponds to a constant induced velocity along the span. It follows that if we are able to distribute uniformly the induced velocity on the rotor, we will have the ideal elliptical induced velocity and we will have the best distribution of the lift. How to do this? How to make uniform the induced velocity? The most used solution in the industry is to twist the blades nose down towards the tip, the so-called washout. Therefore, nose up towards the center. Twisting the blades. Here you see the distribution of the induced velocity and of the lift for an ideal twist and of untwisted blades. You can see that a rotor with untwisted blades have the heaviest loading near the tips. Therefore, high induced velocity outside the disc. If we are twisting the blades nose down towards the tip, as you see down in the figure, it will give you the ideal triangular distribution for lift, which corresponds to a constant induced velocity. If you look as well on the span-wide load distribution for a hovering helicopter, you will see the same. Here you see the radius and the blade loading along the radius of a helicopter blade. The radius is non-dimensionalized, so at the end you have the value of 1. At the end of the blade you see the tip vortex trajectory, and there you see the blade loading increasing. The figure of merit variation with the linear twist, it improves a few percentages. You see in this figure the use of the linear twist as a function of the figure of merit in hover. You see that we are twisting the blades nose down, so we have a minus twist. So you can see that going from a linear twist of 0 degrees to a linear twist of minus 20 degrees, it improves the figure of merit from 0.76 to 0.79. The twisting the blades washout, it will decrease the angle of attack towards the wing tip. And twisting wash in, it will increase the angle of attack towards the wing tip. Therefore, twisting improves the figure of merit by several percent. However, experience has shown that optimum twist for hover performance, which is about 30 degrees, will generate highly oscillatory loads and vibration. Therefore, in helicopters, we use only moderate twists between 6 to 12 degrees. The problem with twisting too much the blades is coming in forward flight. There we have vibration and noise problems. Why? In forward flight, due to twist, the advancing tip is working at negative angles of attack. You see there at the end of the tip a negative vortex which is formed. This will come in the following blade, and then there will be a performance penalty. One has designed also adaptive blade twist. If we are capable of directly controlling the twist of the helicopter blades by using smart adaptive elements or active fiber composites, we will obtain a much better distribution of the blade twist. Here you see the so-called active twist rotor at the NASA Langley with the different regions on the profile, each region optimized to obtain a maximum lift. How to obtain further maximum hover performance? Another solution is to optimize the blade area. Of course, to obtain best hover performance, the airfoil should be flown at an angle of attack which gives the highest lift-to-drag ratio. In this picture, you see the lift coefficient, the drag coefficient, and the CL over CD as a function of the angle of attack. You see that if you force the blade elements to operate at an optimum angle of attack and just below the stall, which corresponds to 8 degrees, one will obtain the best hover performance as the maximum CL over CD is flown on every blade profile. How to optimize blade area? You'll see that if you are going to optimize the blade area, the figure of merit will also improve. For example, here you see the average angle of attack and the figure of merit. You see that if we are going to fly each blade element between 6 to 8 degrees angle of attack, the figure of merit will be in the highest range. How to do this? We can use taper. If you remember, taper, it is defined as the ratio between the chord at the tip of the blade and the chord at the root of the blade. Using taper, it can improve the figure of merit also by a few percentages because it is unloading the tip. So you see here a rectangular blade, and you see also some other practical solution used in helicopter industry. The practical solution is the one that you see in the last picture. If you use no taper, if you use an ideal taper, and then the practical taper for used in the Bell solutions. So recapping, using twist and using taper, it can improve the hover performance by a few percentages. This ends this part of the lecture.